Hello, dear students. With respect to our last video, we have come across with your two of the algorithms there. Okay, one happens to be K-means and the other one was agglomerative algorithm there. Okay, and then comes is your third respective algorithm, which belongs to an another type of clustering, and that's called as density-based clustering there. Okay, so wherein it stands out for DBSCAN. Okay, which is density based scan algorithm there. Okay, so what is ultimately the use of this is always keep in mind there are huge dense number of your respective points which are considered here. Okay, so what do we do here is you eliminate the noise points. Okay, you perform clustering on the remaining points there. Okay, so this algorithm, of course, it's a pseudocode which is given to you. Okay, but apart from this, I'll take an example and explain. Okay, current cluster label is, you'll take it as 1 for all the core points. What you have to do is, if the core point has no cluster label, then current cluster label is equals to +1. We'll increment it. Okay, label the current core point with cluster label current point there. Okay, so which ultimately says that you are labeling the current core point with cluster label current cluster label ndf. Okay, for all the points in EPS neighborhood except ith, the point itself. Okay, do if the point does not have a cluster label. Okay, then label the point with the cluster label current cluster label that ndf and for. Okay, I'll take an example that will be easy to you guys. Okay, these are my original points here. Okay, these are my original points. Okay, so if I go across with the clusters which are formed here. Okay, so these are my respective clusters there. Okay, they are resistant to noise, can handle clusters of different shapes and sizes there. Okay,
Okay, so followed up with that, when DBSCAN does not work well. Okay, so when these are my original points, this is minimum points, this is EPS which has been given there. Okay, so varying density is where you find and very high dimensional data. So at that time you can come across in a situation where DBSCAN does not work well there. Okay, as demanded. Okay. So let us come across with an example here. I'll just take an example and let you guys know. Just go back with an example here. Okay, you can just come across DBSCAN. Okay. Okay, so I've just that was a copy paste work. What I have done here. Okay, it is DBSCAN. Okay. So usually they will give you like perform DBSCAN clustering algorithm on the given sample data and find core point, boundary point, and noise point. Okay, these are the 3 points here. Okay, core points are nothing but any respective cluster which is having the number of core points within it, then it is being stated as that is one respective cluster there. Okay, and a core point which is lying across in one of the respective boundary point, I call this as an boundary point there. Okay, and noise is nothing but that which is not at all included in the respective your traverses there, but even then it has been considered. So they have given here for an problem calling it as minimum points equals to 3 and APS is equals to 1.5. Okay, this is your given data here. Okay, ABCDEF, ABCDEF, these are the data 0, 0, 0. They are one and the same over the diagonals there. Okay, so what's your very first point is core point identification. Okay, so they have said you minimum points should be 3. Okay, just scan this E column. Okay, so how many values are you finding as a least one? 0 is there, 0.7 is there. They have given AB as absolute value to be 1.5. Okay, so there are only 2 points. Okay, so that's why it is not considered. Okay, it's not a core point. It can either be a boundary point or else it can be a noise point. Okay, shift to your B. Okay, so here B, how many of the points are there? One is 0.7, one more is 0. So this also again only 2 of them are there. So that's why it also can be a boundary or a noise. Shift to the third one here. How many points are there? 0 is there, 1.4 is there. So again, it can be a boundary or a noise. Okay, come to D here. How many points are there? One is 0, one more is 1, one more is 0.5. How many points do I have? 3. It satisfies this point called out as minimum points equals to 3. So what do I call this? I call this D as a core point. Okay, similarly, shift to your E now. E, how many of them are there? 1.4 I can take because I have given 1.5 as your EBS. 1 is there, 0, 1.1. 4 of them are there, so I can state this one also as a core point there. Okay, shift to F, 0.5, 1.1, 0. Okay, how many values? 3 values. Again, this can also be treated as my core point now. These 3 are my core points. The same I have written across with your step. Only 2 points, so cannot be a core point here also, here also. It has 3 points, so it's a core point. It has 4 points, it's a core point. Minimum they have given 3, so it can be more than that also. Okay, so this is with your core point identification. How to identify your boundary identification or boundary point identification? Okay, so how to do that? That is, the boundary can be between only 1, 2 and 3, only either of them. Okay, so what you have to do is, with this, just go across with what's the least value apart from this 0. Apart from this 0, fine, just come across with your C. Apart from this 0, which is the least point, which 1.4. Okay, with what respective um, what do you say, axis it is? It's with E. E is already been visited here, so that's why I come to a conclusion saying across as it's a boundary point. Okay, that it's a, because it is traced now, 1.4 is already been traced. Okay, boundary point says that it has to be already a core point, so then you can come across saying that it's a boundary point. Okay, it says that least value to 0 is 0.7. Okay, so and is not visited by B. Okay, so that's why we say that okay, let's come across with C. Okay, next least value is 1.4 here, it's visited by E. E is already a core point, thus C is a boundary point here. Okay, just go with A and B now. Okay, less than 0 is 0.7, which is with A. A is still in an conclusion that whether either it can be a boundary or else a noise. So that's why I come across with a conclusion saying that it's a noise here. Okay, so then here come across with your A. Apart from the 0, which is the least one, 0.7, it's B. Okay, so B is not at all visited yet. Okay, neither a point, anything. So that's why here also I can call it as a noise. Okay, both A and B are your noises here. Just come across, these are my final results now. A is a noise, B is a noise, C is a boundary point, D, E, F are my core points. This is how you'll be using across with your DBSCAN cluster. Okay, I hope so you have got to know with this DBSCAN. Okay, so followed out is with your graph-based clustering. Okay, so I will tell you across in this. This is one and the same almost. Okay, I'll just complete it. Okay, it's fine. Graph-based clusterings are nothing but wherein you say that you are using across with the same proximity matrix. Okay, then you are finding minimum. If you are finding, you are using across with a single link. Max if you are finding, you're finding across with a complete link there. Okay, so usually the clusters are connected components in the graph here. Okay, so we call here as a cure algorithm for graph-based clustering. Okay, agglomerative hierarchical clustering algorithms vary in terms of how the proximity of two clusters are computed. If I'm taking min, I say that's susceptible to noise or outliers. If I take max, it's a complete link. Group average or centroid voids may not work well with non-globular clusters. Cure algorithm tries to handle both the problems. Okay, what does this algorithm say? It represents a cluster using multiple representative points are found by selecting a constant number of points from a cluster. First representative point is chosen to be the point furthest from the center of the cluster. The remaining representative points are chosen so that they are farthest from all the previously chosen points there. Okay, so here I can just come across shrinking. One point is chosen and these are quite very near to the things there. Okay, and call it across with a factor called as alpha. These are farthest one. Okay, I call this with a shrink as a representative point. Okay, cluster similarity is the similarity of the closest pair of the representative points from the different clusters. Okay, so here algorithm says that if my alpha is equals to 0, it is similar to centroid based. If it's equals to 1, it's somewhat similar to my single link. Okay, here is better able to handle clusters of arbitrary shapes and sizes. Of course, there is no any given example on this particular cure algorithm, but this is how your sparsification in the clustering process work. That's a data set I have. I have construction of my proximity matrix. Through this, I construct a sparse graph. Okay, from the sparse graph, I partition that particular graph, and these are my respective partitions. Okay, so you got across to know with this. Okay. Similarly, come across with your clustering tendency. How this evaluation of clustering happens here. Okay, so there are some evaluation tendencies which is given here for evaluation here. Okay, like Hopkins statistic. Okay, that is being calculated for the spatial randomness. Okay, which has been calculated that h is equals to summation of yi. Okay, divided by summation of xi plus yi. Okay, where your respective xi and yi okay, are the uniformly distributed which has with close other. Okay, and h is close to zero point 0.5. D is highly skewed. Okay, h is close to your respective zero there. Okay, so empirical methods are used for determining the number of clusters there. That is root of n by 2 for a data set of n points. If I have n points, so these many clusters can be found there. Okay, there are similarly cross validation method is there. Okay, so it says that divide a given number of data sets into m parts, use m minus 1 parts to obtain a clustering model, use the remaining part to test the quality of the cluster. Okay, so these things can be used so that you will be evaluating your respective clustering there. Okay, and ultimately you'll be measuring it as extrinsic or as intrinsic. Okay, extrinsic says that it's a supervised one. Okay, whereas intrinsic says that it's a unsupervised one. Okay, and I hope so you have got to know with this with respect to your clustering. Okay, this ends your clustering as a module there. Okay, with especially you are coming across with 4 different types of clusterings there. Okay, thank you.